Okay, so I have really only one recitation question to go over for chapter 12. Chapter 12 is a pretty short chapter for us, so doesn't warrant a whole recitation, but there was one more problem that I wanted to go over after looking through the homework that I assigned and comparing it to what we talked about in lecture videos. So it's this one up here on the screen. So we have a guitar string is vibrating at a frequency of 330 hertz, and it has a wavelength of 1.4 meters. And we are going to try to figure out what happens to the frequency and the wavelength of the sound in air as it reaches our ears. Um, so um, the a thing to just commit to memory on this is that as a wave passes from one medium to another, the frequency of that wave never changes. Okay, so we're going to be working with this formula to solve this question. So the speed of the wave is the wavelength of the wave times the frequency. Frequency is in inverse seconds or hertz, and the wavelength is in meters, and the speed will be in meters per second. So what is going on with this guitar string is that there's this string and it's vibrating up and down, and the reason that this vibrates up and down is that it sets into oscillation a sound wave in the air. So there is a vibration that is going up and down at 330 cycles per second. And then that wave is making a transition from the solid of the string into the air. And then that causes our eardrum to oscillate in and out at 330 hertz as well. So this is a general rule about all things waves. As a wave passes from one medium to another, the frequency will never change. So I'm going to write that down. Okay, so what needs to be happening is if the frequency can't change, velocity and wavelength will change in the way to these two things are going to change in a way to answer our question. All right, so one thing that I have sort of committed to memory is that is this thing about the speed of the wave. The speed of a wave tends to get faster as that wave travels in a denser and denser medium. So the speed of a wave, the speed of any wave, so we're talking kind of specifically here about sound waves, but the speed of the wave on the string uh, is a solid, so that's a denser medium than the air. So the speed of the wave kind of is slowest in air, it would be faster in water or another liquid, and it would be faster still in a solid. Okay, so if you don't have that committed to memory, I actually don't have it to pull up on the screen right here, but there's a table in your book that shows the speed of waves in various different mediums, the speed of sound in various different media, so you can always look that up as well. So as the wave passes from one medium to another, the frequency doesn't change, and we will say that V is faster in the string, slower in air. So if we have a big V on the left-hand side of this equation, then that means that we have a long wavelength here. So in the string, right, our waves are longer, right? So V big, wavelength big. And in the air, we have V small. So the wave will have a shorter wavelength. It'll look more like that. Okay, so to answer this question, right, we will immediately rule out B and C because those will immediately rule out B and C because these say that the frequency changes. So we're looking at A, D, and E. And so we have shown that in air, it has a shorter wavelength. So we'll circle E as the answer to that. So the answer to this is E. And that's the only recitation question that I wanted to go over. One other thing that I noticed when I was looking through the homework just now is there's talk and a couple of questions about octaves. And also in your reading quiz question, there was a talk about octaves. So octaves are what happens when you play the same note, but it's a higher version of a note. So let me give you an example of an octave, right? So a low note would be la, la. So I was singing the same note, but there's a lower version of it and a higher version of it. And if you've done things with music, then this is probably something that you just know intuitively. And if you haven't done things with music, then that might be totally new to you and kind of abstract to you, and that's no big deal. But the only thing that you need to know for the homework is that going up an octave doubles the frequency. So if I come over here, right, if we play a 100 hertz low note, one octave higher is 200 hertz. Okay, another octave higher than that, we have to double 200 to get up to 400 hertz. So you notice that I actually skipped 300 here, all right? So it's not that I'm adding 100 every time, it's that I'm doubling my previous number. So another octave higher will double 400 and get up to 800 hertz. And then 12 to 1600 hertz. And that continues. So, so this would be 1 octave higher, 2 octaves higher, 3 octaves higher, 4 octaves higher, and so on and so forth through everything. Okay.